right, it's 3 o'clock. I gotta start talking now. They're only 7 right now. The noon class is almost full. I know some people do watch me online. I got a couple of students who are telling me they rather watch me online. I don't know if that's a personal insult or it's. They say they like to rewind and re-listen and then pause and work things out. So if you're online listening to me, holler to you then. Does anybody have any questions about anything before we start? So the second part of chapter 7, at least as far as the notes, and we were talking about the particle wave duality of things. So photons and electrons have both wave-like and particle-like behavior. So we talked a bit about the particle-like behavior of a photon. Now we're going to move on and talk about the wave-like behavior of an electron. And I'm going to skip the physics of it, but this is the equation. The de Broglie wavelength, you get this from physics, is equal to Planck's constant h over the mass times the velocity, so it's h over momentum. And so what is the de Broglie wavelength of an electron with a speed of 2.65 times 10 to the 6 meters per second? So let's put in the numbers. It's just Planck's constant, 6.626 times 10 to the minus 34 joules times seconds, all over mass of electron. It's 9.11 times 10 to the minus 31 kilograms times the velocity, 2.65 times 10 to the 6 meters per second. Okay, so let's look at the dimensionality of it. So we have joules times seconds divided by kilogram meters per second. So the inverse seconds, oh wait a second, that won't cancel. What am I doing there? I gotta put in what a joule is. A joule is a Newton meter or a kilogram meter squared per second squared. So we have a kilogram meter squared per second squared times a second all over a kilogram meter per second. And the seconds cancel there, inverse seconds cancel, one of the meters cancel, kilograms cancel, and we're left with meters. There's the units. And let's put in the numbers. And I did that while we're waiting for class to start. 2.74 times 10 to the minus 10 meters. Okay. So you're still like, that's pretty small, but that's about half the size of a hydrogen atom. So that's for an electron, that's fairly significant. But let's wait for the question.
Where'd you get the 9.11?
That's the mass of a kilogram, or mass of an electron.
Oh.
So the wavelength is Planck's constant over mass times velocity or momentum.
And they would give us the mass.
Yeah, you don't have to memorize the mass of an electron. So you don't have to memorize the equations either. I give you the equations, give you all the constants. Don't have to memorize Planck's constant. Not doing that. Other questions? Okay. So here's your turn. What is the velocity of an electron with a de Broglie wavelength of 1.2 times 10 to the minus 10 meters? And I'll zoom in on this. Oh, it's massive. Let's see if you can put it in your calculator. London, did you forget your calculator? Right, okay. Some people think A, 3 times 10 to the 6, 3 million meters a second. I think B, 6 million. Okay, so we got half a class, more than half a class going for, yeah, B is right, but are you guys not getting it? Don't use the. Use the second. That's easier. If you use the little e, that's a little more. Did you get it? I haven't seen it. You have to put it around the top because it's the one. Go home. And insert second loop. You have to put it like between them. Because if you do that, you're going to divide by that and you're going to multiply by the velocity. Or you can put a divide sign there. to do parentheses, you have to put it 4, then 9.11, and then multiply that. Divide it. So it's going left to right. So you say Planck's constant divided by 9.11. Then if you multiply that number, it would eventually bring 1.2 to the top. So you put divide again, or you divide with the parentheses on the bottom. That makes sense. Yeah. Sorry for the double, triple, quadruple reinforcement here. It's just, I want to make sure you can put the numbers in the calculator properly. Because that's a real skill, psychomotor skill, brain, psychomotor, motion, hands. But anyways, anybody have any questions? I'll go ahead and, I guess I forgot that we have people at home too. So I'll go ahead and put that there for you so you can look at it. Okay. Does anybody like the show Breaking Bad? Not really. Okay, that's fine. There's a character in there called Heisenberg. At least this is his namesake here, the Heisenberg uncertainty principle. So uncertainty principle here, and this is delta x, delta t. X is position, p is momentum. So the uncertainty in the position times the uncertainty in the momentum is greater than or equal to h Planck's constant over 4 pi. So a couple things in this. You might also see it as h bar over 2 because h bar is h over 2 pi. So you might see h bar somewhere sometimes. H bar is just h divided by 2 pi. And the other thing is, so quantum mechanics has 7 dimensions. So 7 dimensions we work with. And if you have a point in space, we can say that there are 3 position vectors in there. So if you want to, so usually x is either here or up here, whatever, x, y, z. So this point you can describe it in 3 dimensions, saying where it is in position with 3 positions. So x, y, and z. Then there's momentum, so this point here, is it moving this way, that way, that way? So there's 3 dimensions to describe where it's going. So 3 dimensions for position, 3 dimensions for momentum. Anyone want to guess what the 7th dimension is? Time. Time is the last dimension for quantum mechanics. Other theories have different dimensions, but 7 for quantum. And with this, this relationship comes from linear algebra. So this is just a purely mathematical relationship. And there are some effects with this. So there's a range, how well you can know where something is and where it's going. And if you force something to know exactly where something is, you have no idea where it's going. And if you force yourself to know where something is going, you have no idea where it is. So let me show you an example of that real fast. Then I'll talk a little bit more of the uncertainty principle. So this right here, this quantum mechanical probability distribution, you are greatly deciding where the momentum is going, and from that you have no idea where the particle is. So that's an example of that. But let me go back to the uncertainty principle real fast. It works for more than just position and momentum. It also works for delta E, delta T, so change in energy and change in time. And we see this with ultra-fast laser pulses, so we get laser pulses down to attoseconds, really, really fast. And the energy spread of the laser pulse is very broad. So the photons coming from that laser pulse can be anywhere from infrared to ultraviolet. It's not a set wavelength there. Where you have much longer wave laser pulses, like even picoseconds, so you can get picoseconds to energies to be very exact. But getting down to attoseconds, the photons have spread of energies. It doesn't make any. You can't get it to be anything inexact. So that's the uncertainty principle. This, like I said, it works with energy and time. This is above and beyond the course, but you can look up something called Feynman diagrams. and there are certain processes that the effect can come before the cause. So to give you an example of that, so you can, when you look at your image in the mirror, what's happening, so I look at my face in the mirror, and what is happening, the light is coming from the lights, it's shining on my face. The light that's not absorbed by my face is reflected to the mirror, and there's silver metal in the mirror, typically for many mirrors. Sometimes they have aluminum. But either way, metal surface, the light comes from reflected off of my face. The electrons in the metal absorb the photon, and then they emit it back out. That's the reflection. It's a photon in, photon out process. And you can, the metal can absorb a photon and emit a photon at the same time. It can also absorb a photon, wait a little bit, and emit a photon. It can also emit a photon, wait a little bit, and absorb the photon. So you can have the effect happen before the cause. That can only happen on very, very tiny timescales, though, and for very specific instances and particles. It's not like my face hurts and then you punch me. It doesn't work like that, right? That doesn't work for big things like us. But for tiny things like electrons and photons, you can have certain radical things. So the uncertainty principle, although it does apply to us, I mean, it doesn't really, because we're too massive. So, and the quantum, we don't have quantum effects. We have what's called classical effects. And here's an example of a classical effect right here, the classical trajectory. So I'll start with the first one over here. This is like you throwing a basketball. So if I take a basketball and I throw it, it's going to follow a parabola, right? And if I were to shoot an electron, like I mentioned, this is a case where you know the momentum very well, you know where you're going very well. The probability distribution of the position is fuzzy. You have a very limited, since you've defined the momentum, you have very limited understanding of where the electron or whatever particle, a proton, you've thrown in that direction. And a misconception is that the proton's just moving around, or electron, or whatever you have. It's not. It's in all those places at the same time. It's kind of this fuzzy existence. And that's different, of course, to us. We're used to solid things. You know, I'm used to my water bottle looking like this and has a set shape. Electrons aren't like that. Electrons, there's an uncertainty in their position of momentum. And we can't really know. You can't ever really know. So the way this strike zone is another way of saying that there's a probability for things. That's a picture illustration of that. I'm not really into sports, so I actually prefer the quantum. So for me, myself, when I think of an electron, I think of it, looks like a football to me. Well, here I'm using a sports metaphor. It's kind of shaped like a football. Well, an electron that's just absolutely not moving, zero kinetic energy, it's a sphere. But most electrons are going somewhere. They're usually not sitting still. And I see it as kind of, the probability is mostly in the center, but I'm trying to shade it in quickly, that to me, an electron, if you wonder what I see an electron as, if it's floating through space, I see it kind of like a football, maybe even a little longer, and it has quite a bit of density in the center, but it has a little bit less going out to the edges. And it's shaped like a football because it's usually, if it's motion somewhere, it's gonna become more prolate. Also, if you speed electrons up really, really fast, like at a particle accelerator, getting really close to the speed of light, the electrons become very thin and narrow, and it's with partially the uncertainty principle. Their time, they become very flat, and they exist over a long stretch. And when that happens, you can almost stack them on top of each other. So electrons tend to repel each other, but when you make them go really fast, like in a particle accelerator, you can make them stretch out very thin, and they're very diffuse in their charge, so that way they don't repel each other as much. So, but most electrons are not in particle accelerators, unless they're orbiting a black hole. Then they're essentially in a particle accelerator-like behavior. Okay. So, and well, coming up soon, we're gonna have you're gonna have a kind of a many students find a kind of a mind-blowing experience with some of the quantum mechanical model. We're not there yet, but let me show you some of the background. Now, this is also tends to be well, this is above and beyond the course, but some of it is, some of it isn't. But maybe you've seen this is the Schrodinger wave equation. And the Schrodinger wave equation is H, the Hamiltonian, H psi equals E psi, the Hamiltonian operator on the wave function shoots out the energy levels and then the wave function again. So Hamiltonian, it's an operator. So what the Hamiltonian is, it's the kinetic and potential energy of the electron. And an operator, so these four things, these are operators, the plus, minus, multiplication, division. So if you see 1 plus 1, the plus sign is an operator that you say, okay, the number 1 is operating on this other number 1, saying that I should add them together, and then by adding them, I get a new number 2. So that's the operations. Here, the Hamiltonian is operating on the wave function, and in this operation, just like the plus, minus, multiplication, divide, the energy levels pop out of it. This is, and you'll learn about this if you go to study the matrix algebra. The energy levels are also known as the eigenvalues of the matrix. So it pops out the eigenvalues. It's also how our computers solve equations. It's Gaussian unknown. That's one way you can get the eigenvalues of a matrix, and it's typically how the calculators and computers solve for unknowns in our whatever computer programs. And the wave function pops back out. So later on, we will talk about the energy, the probability distributions of this, the pictures of the wave functions. This is the integral from negative infinity to infinity of the wave function vector dot product with its complex conjugate, and d tau, that's just all space. So dx, dy, dz can be d tau, or it can be polar or spherical coordinates if you studied those. So the complex conjugate, so a complex number is a real number plus, so a real number is just any number that's not imaginary. So imaginary number is something to do with I. If you've heard of I, it's the square root of -1. So now the imaginary numbers, it's a flaw in our mathematical number system. Now mathematics is a very powerful model, but there are some issues with it. Like for instance, it's very difficult to divide by 0. And I is another one, the square root of -1. We call it we call it I, the imaginary number. Now it's not that there's nothing wrong with I. It's just, like I said, a flaw in the mathematical model. But I is still useful because imaginary numbers, are what give cyclic things to happen in mathematics. So I to the first power is I, square root of -1. I squared, -1. I cubed is minus I to the fourth is 1, and I to the fifth is I. So you can get cyclic natures of things by power laws. So that's where things like a sine wave, you get the cyclic nature of things, you can describe it using imaginary numbers. So just by using a power sequence and imaginary numbers, doing that. So a complex number is just a real number, which means not imaginary, plus or minus an imaginary number. So so a complex number would be like 3 plus 2i. A complex conjugate would be the opposite of that, meaning so it would be 3 minus 2i. So if the regular number is 3 plus 2i, the complex would be 3 minus 2i, and vice versa for minus to plus. And if you do that, you get the probability distribution of the wave function, the electron cloud. So we can show you some of those pictures later. I think they're cool. I think they look really nice. I don't know if we'll get to that today. We didn't in the last class. We stopped right before there. Now, so this stuff that I just mentioned with all the complex conjugates, this is above and beyond this class. If you study physics, you can learn about it in your junior year, or you can be like me and learn about it in graduate school if you go into chemistry. So now if you solve, this has already been solved. You don't have to do all the math, don't worry. You get the solution for the hydrogen atom. This is the solution for the hydrogen atom. The e to the n energy level, so energy level n is 1, 2, 3, 4, 5, whatever. We'll talk about n soon, is equal to the Rydberg constant, which is 2.18 times 10 to the minus 18 joules. You might also see the Rydberg constant written as a wavelength. So you can get it in inverse nanometers, for instance, or nanometers, depending on which one you use. So if you look up the Rydberg equation, this is known as the Rydberg equation as well. If you look that up later on, if you look at up other things and other sources, you might see it as something else. And then the 1 over n squared, we'll start talking about the n soon. And some definitions. A free electron, we say a free electron just sitting there in space, not bound to an atom, has 0 potential energy, and a bound electron has negative potential energy. And we do this just to make the math easier. So we could pick a 0, or we could pick the lowest energy level, say the 1s electron in element number 118. That's a very low. We could call that our 0, but then we'd have to relate that to all the other electrons and all the other orbitals. So to make it not, instead of doing 2 calculations, we just want to do 1. We just say, well, the electron that's already ejected has 0 kinetic energy or 0 potential energy, and everything else has negative. So the negative energy is just a way to make our math easier. So, all right. Now here comes the mind-blowing part. So hold off your thoughts for a little bit, or your questions, I should say, when unless you need a clarification question. This is one of those things I'll explain to you. It'll seem kind of weird, and then when you think about it for a while, take a nap, go to bed at night, next day you wake up, it'll probably make more sense. So in this here, are you ready? We're about to start the quantum mechanical model of an atom. So this here is the quantum mechanical model for the atom. And we're going to start by defining some quantum numbers. The first one is n. We're going to call this the principal quantum number. And n can exist as positive whole numbers. So, and this is discrete mathematics as well, so it's only whole numbers, not anywhere in between. So n exists as 1, 2, 3, 4, 5, on up into infinity. So positive whole numbers are what n exists as. And I'm going to define a second quantum number, the angular momentum quantum number. And the angular momentum quantum number exists as positive integers and 0. So positive integers and 0 up into n minus 1. So meaning, if n is 1, L can be 0. There's only one choice for when n is 1. If n is 2, L can be 0 or 1. If n is 3, L can be 0, 1, or 2. If n is 4, L can be 0, 1, 2, or 3. So up into the number n minus 1. And slinking ahead, we have a couple things. When L, for an electron, when L is equal to 0, the angular momentum, we call this an s orbital. This is left over from what's called the Bohr model. Maybe you've seen the Bohr model. When you see this is, okay, that one looks a little better. Maybe you've seen atoms look like this. You've kind of seen that. That's the Bohr model. That's when they thought that electrons were like planets orbiting a star. And then certain orbits can only hold so many electrons, and that was the Bohr model. It was a very, very good model, fundamentally wrong. So we're keeping with the Bohr model by calling these orbitals not orbits, but orbitals. So L equals 0, that's an s orbital. L equals 1, that's a p orbital. L equals 2, that's a d orbital. And L equals 3, that's an f orbital. S stands for sharp, p is principal, d is diffuse, f is fine. These are old school spectroscopy terms. The s orbitals are very easy to see. They're very sharp peaks. The p orbitals are also easy to see. They're not as sharp as the s orbitals, but they're pretty good. Diffuse gets harder to see, and fine, you have to break out your magnifying glass to see those on the paper printout. So these are old school spectroscopy terms that we've kept. S is not spherical, P is not perpendicular, although some people think that it is. It's sharp, principal, diffuse, and fine. But okay, so let's move on. So we've talked about the angular momentum quantum number. Let's talk about another one, the magnetic quantum number. So M sub L. M sub L, this one exists between minus L plus 1, up through 0, 1, 2, steps up to L. So we have N that exists as positive integers, without positive whole numbers, I should say, not 0 is an integer. Positive whole numbers. L are 0, or can be 0, and positive integers up into n minus 1. M sub L is bound by L and can be steps from negative L, integer steps through 0 included, up to positive L. Well, L is positive, so meaning, let's say L is 0. M sub L has to be 0. Let's say L is 1. M sub L can be minus 1, 0, and 1. If M sub L is 2, if L is 2, M sub L can be minus 2, minus 1, 0, 1, 2. If L is 3, M sub L can be minus 3, minus 2, minus 1, 0, 1, 2, 3. Is this making sense? Okay. Now the last one is the spin. This, if you read the textbook, the spin is not covered in chapter 8. I cover it now because it's a quantum number, and I think it fits in better now. The spin of an electron happens to be a fermion, which means that its spin is the ratio of two integers, and the result is not an integer itself. Like 2 over 2 is a ratio of two integers, but 2 over 2 also equals 1, right? So, but 1/2, electrons have a spin of 1/2. So, okay, what does this mean? What is the spin? So an electron, we've already talked about, has this uncertainty of position and momentum. The electron, though, has a magnetic field, okay? And the magnetic field is pointing all over the place, but for the overall magnetic field, it will sit and point in a specific direction. So that is the spin. It's not like it says spin up. It actually moves all the way around. But it's not even just an overall, it's not just a one vector. There's magnetic fields going all over the place, but if you sum them all up, they point in a specific direction at a given time. And it moves. It moves various points in time. And the plus 1/2, minus 1/2, why do we have to have that? It's because the Pauli exclusion principle, so no two fermions may have the same set of quantum numbers in the same atom. So Pauli exclusion principle right there. And this here is the reason why matter has structure. So it's from the Pauli exclusion principle. So light and other things are bosons. So light and energy is a boson. Bosons have integer spins. They do not have the Pauli exclusion principle apply to them. So the electrons, they have the Pauli exclusion principle. So that means for a certain orbital, there can fit only 2 electrons, one with a spin plus 1/2, minus 1/2. It just means that the magnetic field is pointing opposite the other one. That's all that's saying. And they can occupy 2, so you can have the same orbital can occupy 2 electrons at the same time. But they have to have different spins, because otherwise it would break the Pauli exclusion principle, and which is why I can't put my hand through the desk, because the electrons in my hand are approaching the nuclei of the atoms in the desk, and as such the electrons will try to populate the orbitals along the nuclei in the desk. There's already electrons in them, and they say, no, man, I'm already here. And then if I try to apply pressure, what happens is they push back. And because they push back, matter has structure. This is also known as electron degeneracy. So if you've ever taken astronomy, there's electron degeneracy. So white dwarfs and brown dwarfs, they're stars, and a brown dwarf has lost all of its well, I guess white dwarfs too. They burn all their fuel, and they're just cooling down, and so they're not producing any more nuclear fusion. So what's keeping them structurally together as a star? Well, gravity is pulling them in, but then the electron degeneracy pushes it out and gives it structure. If there's too much matter, you can break the degeneracy and you can form a black hole. So can you break the Pauli exclusion principle? Yes, but you need to have something on the order of a black hole to break that. You need something really, really powerful to break the Pauli exclusion principle. And okay, so let me go back up. So let me talk about something real fast. Then I'll go back up to the quantum mechanical model. So bosons of integer spins, they do not follow the Pauli exclusion principle. So you can have bosons with the same set of quantum numbers and the same atom or situation. So in a single point, you can put all the photons you want. So you can really, really concentrate light down. So we can have very powerful laser pulses. So I think I told you in grad school I had a 2 gigawatt laser. So, and that was that. I mean, it was a picosecond. It was a 15 picosecond. It was millijoules at 15 picoseconds. So a really, really short time. But I mean, a gigawatt. That's so. A watt or Maui's power output's about 350 megawatts, so it's about 6 times the energy production of this island, put into a really, really small time spot. So you could focus that down. I mean, using lenses, so you can put all that down to a really, really small point. So you can stack light up in a very tightly packed thing with not any problem. Can you imagine doing that to matter? I mean, you can with like a neutron star, like I said, or I mean even more specifically a black hole, but you can't do that with matter. You can do that with light, not a problem. But there's something called a Bose-Einstein condensate. Have you ever heard of that? This is above and beyond this class, but so certain nuclei are bosons. So heavy hydrogen deuterium is a boson. So the proton-neutron combination of the deuterium nucleus, that's a boson. But they've gotten a Bose-Einstein condensate to form from ruthenium atoms. This was in the University of Colorado. They got them close to absolute zero, and they were able to stack ruthenium atoms in the same space at the same time. And they had this. It's a Bose-Einstein condensate. They were able to form one. And that's because, so you can take matter, fermions that have spins of a half. So protons, neutrons also have spins of 1/2. You can gather them together, so 1/2 plus 1/2 is 1. So you can take 2 electrons, a proton and a neutron or something like that, you can form a boson from that. And then if it's a boson, you can stack them on top of each other. And this is believed to be how superconductance works. So electrons flow through wires and they have resistance. The resistance comes from friction. It's just the friction, and specifically the Pauli exclusion principle. Like I said, you can't have the same set of quantum numbers. So what we believe is the electrons are doing is you're having 2 electrons joined together. 1/2 plus 1/2 makes 1, and they turn into a boson. And then they can undergo a Bose-Einstein condensate, and then they flow without resistance. So we think that's how superconductivity may work. We're not sure. Superconductivity does work because there's a superconductive magnet in an MRI machine. So we can get it to work. We know we can get it to work. We just don't. We're not really sure what's happening. We think it has to do with that Bose-Einstein condensation phenomenon. Okay. Let me go back up and talk about these orbitals, and you'll learn about this in the next chapter, but I will introduce it now. The periodic table here. These are the s orbitals. So +1, plus 1/2 minus 1/2 spin. S is when L is 0, and m sub L has to be 0. This here comes from the p orbitals. When L is 1, m sub L can be -1, 0, or 1. And in each case, you can fit 2 electrons in the orbital. These are the d orbitals here. So there's 5 available, 10 electrons. So L equals 2. So m sub L can be -2, -1, 0, 1, and 2. And F orbitals are when L equals 3. So -3, -2, -1, 0, 1, 2, 3. So we're going to show you the quantum mechanical model applies directly to the periodic table. And the periodic table is set that way. The ends are the rows. So the first row is n equals 1, second row is n equals 2. It gets a little fuzzy at n equals 3. We'll talk about that in the next chapter. But that's why the periodic table is shaped that way. Kind of curious. Okay, so there's a quantum mechanical model, and it seems so simple. It's so simple, yet it's very powerful. Where you have n, the principal quantum number, and then you have L, which is bound by n, can be 0 up to n minus 1. Then you have a magnetic quantum number where it's bound by minus L integer steps, including 0 through positive L. And the last one is a spin, plus 1/2, minus 1/2, Pauli exclusion principle, which is the reason why matter has structure. And we're not just all, just collapsing under gravity. This is our electron degeneracy right here. I know you like astrophysics. And yeah, so let's look at some of the questions here. What are the quantum numbers and names of the orbitals and the n equals 4 principal quantum number level? How many n equals 4 orbitals exist? So from the Bohr model, n squared equals the number of orbitals. So I already know that it's going to be 16. But I'll go ahead and verify that for you. And that's left over from the Bohr model. 4 squared? Yeah, because n equals 4. N squared. 4. What?
Where's this?
Oh, that's from the Bohr model. That's not listed in there. I'm just telling you that that's what the Bohr model will predict, and it actually will be 16. But I'll show you. Okay, n equals 4. We have n equals 4. L can be 0. And if L is 0, m sub L equals 0. Okay, so L can be 1. If that happens, m sub L could be -1, 0, or 1. L can be 2. M sub L can be -2, -1, 0, 1, and 2. And L can be 3. In this case, m sub L could be -3, -2, -1, 0, 1, 2, or 3. So the names of these orbitals, this is the 4s orbital. That's when L equals 0. And you have the 4 as the principal quantum number. 4s. This would be the 4p orbital. This would be the 4d orbital. And this would be orbitals. This would be the 4f orbitals. How many orbitals are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 orbitals. Which can hold 2 electrons apiece, so it can hold 32 electrons in these orbitals. So, anybody have any questions on how to do this?
Can n be 5?
Yes, n can be 5. If n is 5, then you would have 25 orbitals or 50 electrons that could populate that. We don't have a name for the fifth. We would call it the G. Yeah, I guess we call it the G. Because then we just go alphabetically after that. We don't have a name for it. Because F is fine. So, but then it would be G, then it would be H, and I, J, K, L. Other questions? You do see the G in higher electrons in higher L's in nuclear physics. So the protons and neutrons do go up there much higher. Okay. So now we have these set of quantum numbers specify an orbital. One set is erroneous. Which one and why? So I'll zoom in on these. So n equals 3. That means L can be 0, 1, or 2. L being 0 is fine. If L is 0, M sub L has to be 0. So A is fine. All right, so B. N is 2. L can be 0 or 1. L being 1 is fine. If L is 1, M sub L can be -1, 0, or 1. -1 is fine. That's good. If N is, we're at C now. If N is 1, L has to be 0. If L is 0, M sub L has to be 0. So that's fine. Now for D, N equals 4. L can be 0, 1, 2, or 3. L being 1 is fine. If L is 1, M sub L has to be -1, 0, or 1. M sub L being -2 does not work, so D is the one that's erroneous.
The erroneous just mean wrong.
Yes, yes. Error. It's full of error. Kind of British. I'm in error. Okay, and which may be confusing because I've just done this up here with n equals 4. And right, this is n equals 4 for part D. And you can see that there's 2 orbitals that do have M sub L being -2. But that's when L is 2 or 3, right? When L is 1, you have to, when L is 1, M sub L can only be in this category. Right? Okay. How are we doing? Anybody have any questions so far? All right. Which set of quantum numbers is erroneous? That's kind of the wording they use on the tests too, so I'm trying to also, so you're like, what does erroneous mean? It sounds kind of snootish, you know, like it's a Grey Poupon. Well, do you guys know that commercial? You don't know that? Okay. Geez, I'm showing my age. We're talking in lab today. I was telling everybody about the joys of being in your 30s. They didn't seem very convinced. Some people think that A is the wrong one. B is wrong. C is wrong. D is wrong. All right, you guys get it. Okay. D is wrong because if L equals 1, M sub L has to be -1, 0, or 1. So, questions with this? Okay. All right. So, to explain the next part, let me have a different example. Okay, so I'm going to talk about excitation and relaxation. So let me use an analogy instead of this. Does anybody have a favorite TV show? I tend to like Game of Thrones. Does anybody have a favorite TV show?
Yeah.
Office, okay. We're going to throw an office party. You guys are all going to come to my house, and we're going to watch The Office. And I don't, but let's just say for chemistry's sake, I got a sweet lazy boy that's right in front of the TV, prime viewing spot. Behind that, I got a comfy couch. And behind that, I've got some chairs, nice hard wooden chairs. And then behind that, if there's too many people, we can stand behind the chairs. Okay. So let's say you're the first one to the party, and all the seats are open, and you can choose where to sit. Where are you going to sit?
Okay.
The lazy boy, right? And as more people come to the party, they will then occupy the different ones, right? So, and so, right? What's going to happen if the person on the lazy boy gets up and like leaves the party? What's going to happen?
Someone's gonna move
Yep, someone's going to sit down. It can be. And what's that person going to do? Been standing up, watching the third episode of The Office, tired of standing. What's the person going to do when he or she goes a lazy boy?
everyone else is gonna move one.
Well, it depends on. You can have. They don't have to shuffle them all. One can go from one to the other. So you don't have to. It doesn't have to be a massive reordering.
Okay, so
It can. It doesn't have to. So it's not like there's a hierarchy where the couch says, "I want that now." But my point is that person's going to relax. Sit down. You're like, relax. So let's use the same idea, but instead we have the nucleus of an atom, and then we have discrete energy levels as predicted by the quantum mechanics. So you have an electron sitting down here in the nucleus, and you can get it to an excited state. So, excited state! I'm excited! I'm high in energy. I know that raised my voice. Now I'm losing my voice. So you can excite an electron. This is known as an excited state as drawn on the right. An electron is not in the ground state. So what do I mean by ground state? So if I told you I want you to do the same thing for 12 hours. So I want you to pick an action. I want you to do that action for 12 hours. What are you going to pick? Sleep or lying down, right? Who's going to say, I want to carry 50 pounds on my back as I'm climbing stairs? I want to do that for 12 hours, right? Like if you're going to pick something, you're going to pick a low energy state. So electrons are much like people, they like a low energy state. So the reason, if you're wondering the reason for that, is actually it's thermodynamics. It's the second law of thermodynamics. Entropy. Entropy deals with states. So having an excited state means you put more energy into an electron. And so it's concentrated energy into a certain electron. If the electron is in a lower state, it can release the energy and it can spread across the surroundings. So it's probability-wise, it favors having low energy states in many of them versus a few high energy states. So much more likely to have that happen. So but I mean, it's at the same time, it's kind of intuitive, right? I don't really want to be excited. I'll get excited, but I don't want to be excited forever. You know, I want to take it easy sometime. And, you know, more frequently, you know, I do take it easy quite a bit. So electrons the same way. They like hanging out down there in the ground state. Okay, so you can excite an electron up to an excited state. How do you excite an electron? Well, you can do it with a chemical reaction. That will excite an electron. You can do it with radiation. So typically visible light can excite electrons. Also, electronic discharge. So just like the tubes here, the fluorescent lights, there's mercury in them, and we're shooting electricity through them like a lightning bolt. The electronic discharge is exciting the mercury atoms, so it can excite electrons that way. You can also do it with heat, so you can put something in a flame, and it'll excite up the electrons. So those are the ways you can excite up an electron. And then after the electron is excited, it can then go down in various states. It doesn't have to go into like if you have multiple electrons, say an electron there, it's this one could also go down as well. So it doesn't have a hierarchy like you suggested. And then the low energy jumps. So conservation of energy. So if the electron loses energy, the energy has to go somewhere. It gets emitted by radiation. It goes out by light. So a low step is a red or maybe even infrared, and then a high jump is violet, or even a very, very big one can be ultraviolet. So now let me compare this to the excited states here. So this is just what I said. Electron in the ground state, A equals 1. And this is for the hydrogen atom. So the hydrogen atom, N equals 1, that's the lowest energy state. And the hydrogen atom you can, or hydrogen-like means 1 electron. So you can have like a uranium plus 91, for instance. You have 1 electron and then a plus 92 center. So uranium plus 91 would be a hydrogen-like atom. So the electron can jump up by excitation, and then when it comes back down in levels, it'll emit radiation. And for the hydrogen atom, and this is the hydrogen, not hydrogen-like, plain old hydrogen atom, and the you have here the N equals 1, N equals 2, up to N equals infinity. So ionization means the electron is ripped off. Remember, ionizing radiation is a radiation that can ionize electrons. And having excited state down to the N equals 1 level, these are actually all ultraviolet. This is known as the Lyman series, if you ever heard that before. Then there are 4 visible transitions. There's one more not listed. This is known as the Balmer series, the visible one. And then there are others that are infrared. So if you remember, I talked about the spectrum. I said that ultraviolet causes ionization, which is true. You can see that here. And visible is electronic transitions, and infrared is heat, vibrational. You can have this kind of fuzzy, right? So ultraviolet can involve electronic transitions. Infrared can also be electronic transitions. What class wouldn't be unless I told you something and I told you that there was an exception to that, and then there's some other exceptions to that exception, and there's certain circumstances. So that's why people love chemistry. I think it's cool, but a lot of people don't like that as much. So, okay, now I remember our eyes are not spectrometers, so that's what we would see. Here, I'll show you what the spectrum of hydrogen looks like. Hydrogen's spectrum is here on the right. Has the red line, has the teal, has the blue, and has the violet. There's 4 lines there. The visible. That's the Balmer series. Hydrogen, though, if you look at it, it looks like a pink lamp. It looks like a fuchsia pink color. Let's see here. Can I see a picture of a hydrogen discharge tube?
Find any matches
There we
in
go.
Photos library.
That's what it looks like. And it looks kind of pink. And if we were spectrometers, we would see the 4 lines. But we don't. We see them all at once. Okay. So you're starting to get this. We have the electrons can be promoted up in energy levels. That's excitation, high energy. And then when they go back down in energy, they relaxation, down in energy. But then there has to be the change in energy has to go somewhere because conservation of energy, it goes away via a photon. And then if you remember this equation up here, where is that? So this equation here describing the energy levels, E to the n is the minus Rydberg. The minus just says it's negative potential energy. Doesn't mean anything. 1 over n squared. So then we have so delta n, change in n is final minus initial, always. And there we have that. So questions so far about how this works? Let me do an example. Determine the wavelength of light emitted when an electron or hydrogen goes from n equals 6 to n equals 5. So that means that the 6 is the initial and 5 is the final. I've highlighted those in different colors there. So then this would be delta E is equal to minus the Rydberg constant 1 over 5 squared minus 1 over 6 squared. So let me look at this. 1 over 25 minus 1 over 36. Is this a positive or negative number? The 1 over 25 minus 1 over 36. That's a positive number, actually. So one over 25 is a bigger number than 1 over 36 because the number being on the bottom being bigger. Look at it. Think of it this way. What about 1/2 minus 1/1000th? Right. So having a big number on the bottom makes the overall number smaller. Right. So when you have this 25 being a smaller number than 36, 1 over 25 is a bigger number than 1 over 36. So this number is positive. Which means that the electron is losing energy. So the electron going from 6 to 5, it's losing energy. It's losing potential energy. But the energy loss, this is the delta E, I should say delta E electron. But then the energy of the photon, this is going to be positive R infinity 1 over 25 minus 1 over 36. Because the energy loss of the electron is going to be transferred to the photon. Does that make sense? What?
Just trying to
Okay. Think of it like the system. We talked about system last time. If I pick up some ice cubes in my hand, the energy flow, my hands feel cold. Actually, what's going on is the energy, if you look at my hands as a system, energy is leaving the system going in the snowball. That's the negative direction. For the snowball, that's the positive direction because it's absorbing heat. So the electron becoming more bound is losing energy. The energy flow is negative, and then that energy is turned into a photon, and that's a positive energy. So energy lost by the electron turns into the positive energy of a photon. Does that make sense? Not really? Okay, let's...
Just to remember, it's just like to remember that, like a small number, or like 5 squared minus 6 squared, or 1 over 5 squared minus 1 over 6 squared is going to be a loss.
Because there's a...
Because in my head it seems like a gain, but...
Because there's a negative sign right here.
Okay.
Yeah, that's where the loss comes in. But if you think of it money better, let's say that I'm I'm throwing money away from me, right? So instead of money, it's energy, of course, but I'm losing money, but then that money turns into, positive flow away from me of sorts. So that instead of dollars flying out, think of energy, and then that energy turns into photons. So what happens when an electron just spits out energy? It turns into a photon. Does that make sense?
Yes.
Okay. All right. So now we have the energy of the photon. And do you remember we did this earlier in the chapter where energy equals h nu equals hc over lambda? Do you remember that, the wavelength? And then this implies then that the wavelength is hc over energy. So I can write this again. hc over energy equals Planck's constant 6.626 times 10 to the minus 34 joule seconds. C, speed of light, 3 times 10 to the 8th meters per second. All over the energy, the Rydberg constant, I'll just put in the numbers, 2.18 times 10 to the minus 18 joules times 1 over 25 minus 1 over 36, like so. And if you look at the units, joules cancel, seconds cancel, and we're left with meters. So let me do this, 6.62. So this is 7.46 times 10 to the minus 6 meters, which equals 7460 nanometers. Like that. So recap, we have then n equals 6 going in n equals 5, and the electron is going from n equals 6 down to an n equals 5 level, and when it does so, it's going to emit a photon. Of course, it's not visible, but I know it's infrared. So, and the energy loss, so the electron is losing energy. So how much energy does the electron lose? It's losing 1 over 25 minus 1 over 36 times the Rydberg constant. So that energy loss equals the energy gained by the photon. So what's the wavelength of that light? It's going to be, the wavelength is Planck's constant h times c, the speed of light, divided by the energy of that photon. Energy of the photon we've already mentioned there. And putting in the numbers, we get 7,460 nanometers wavelength of that light popping out. Does that make sense? People are thinking. you'll get the I do post this stuff, so. Okay. All right, let's have an easier one. What is the energy of a photon emitted as it goes from the n equals 3 to the n equals 1 level? What is 1 minus 1/9? Some people think that this energy change of the electron, or the energy change of the electron, or the energy of the photon, is equal to 1/9 Rydberg. How many think it's 2/3? How many think it's 8/9? Okay, everyone's going for that. So it's just final is 1. So 1 over 1 is 1, even if it's 1 squared. And 1 over 3 squared is 9, so 1/9. So 1 minus 1/9 is 9/9 minus 8/9. I'm sorry, 1/9 minus 1/9. 9/9 minus 1/9, which is 8/9. So, questions with this one? Oh, that's strange. We're not going to get as far as the earlier class. Doesn't happen typically. Okay, I already mentioned that the orbital shapes are this integral from negative infinity to infinity of the wave function times constant vector dotted complex conjugate over all space, d tau all space. And if you do that, what you find out, and then you can then apply the shell model. So the probability density is this. You have an asymptote, so the probability of an electron being somewhere approaches infinity as you approach the origin. And this is r, distance, so distance from the origin in a sphere. So it approaches infinity. Then you can apply what's called the shell model, which means you integrate as a shell. So kind of like if you like Shrek, ogres are like onions. They're layered. So you haven't seen Shrek, or you don't remember that part? Oh. You have to. Your homework is to rewatch Shrek.
Cool.
The first one.
Okay.
But he says, like, ogres are like onions. We're layered, and just like an onion is layered, if you look at the layers you integrate out in a layer going out, you get a graph that looks like this, or at least you get the radial distribution, and this is for the 1s. Oh, it's already there. The 1s electron has a radial distribution of this, where you have a maximum, but then if you notice, there is a little bit of density really close to the origin. And this actually means then that you find electron density inside the nucleus, which if you took chemistry in high school, they probably told you that there is no electrons in the nucleus of an atom. And it turns out that's not true. So there is electron density in the nucleus of an atom, just not very much. And it's most pronounced for the 1s electron. And this is the effect why this little bit of electron density in the nucleus of an atom, so isotopes, so same number of protons, different number of electrons. The electronic structure of different isotopes for the same atom are slightly ever so different because of this stuff. All right, we'll pick up there. There's my shut up alarm. And I will see you guys on Wednesday then.